Hi there, my name is Cy Brand, I'm the team C++ developer advocate, and today I'm going to tell you how debuggers work. Now, debuggers are a huge subject. You could write an entire book about them. In fact, I already did, and you can go order it from No Starch Press if you're interested. It's like 750 pages, so it's going to give you a lot more details than this talk will. I'm going to keep things at a very high level today, just to give you a flavor for how all of these systems really work under the hood. First of all, what kind of debugger am I talking about? For this talk, I care about native code debuggers for compiled languages, like, of course, C++ and C, but also Swift, Rust. They all work broadly in the same way. Some examples of debuggers you might use are the ones in your IDE, like if you're using Visual Studio or CLion, or a command line debugger like GDB or LLDB. I'm also going to use Linux for most of this talk to discuss the details, but most of the details kind of are applicable to other operating systems as well. This is the agenda I'll be sticking to. We'll start off with a look at the architecture of the usual debug scenario. What are the components of the system that we care about when debugging? And then we'll walk through a bunch of different scenarios and how they work. How does a debugger manipulate memory, or set a breakpoint, or read a variable, call a function, debug optimized code? We'll walk through all of these in varying levels of detail to give you a flavor for how they work. Starting off with the debug scenario architecture. These are the main parts of the system that we care about. We care about, of course, the debugger that we're interacting with. We care about the process that we're trying to debug, which consists of code and the data that code is operating on. We care about the binary file, the executable that the process was launched from, which has that code again, but also debug information. We'll look more at debug information throughout the talk. We, of course, care about the source code we wrote, which will be in C or C++ or whatever, and the compiler will have generated the binary from that source code. Note that there are no horizontal arrows between any of these processes. All of them have to go through the operating system in order to communicate with one of the other components. And, of course, the operating system also provides us a way to interact with the hardware for example, registers, which are very fast, small pieces of memory that live on your CPU and hold things like what the value of the instruction pointer or program counter is, or some of your variables, things like that. Now, the debugger is debugging a process that consists of machine code and binary data, but we usually don't care so much about that representation. We want the representation of our high-level source code. So a lot of the different parts of a debugger have to do that mapping between the process that's running the existing machine code and your high-level source code. And we're going to look at that in a few different ways. Let's start off with manipulating memory. So back to our architecture diagram here, we're talking about the data inside the running process. Also the registers in the hardware, but most of the time we care about that data in the process. And the way that we get at this data, or the way that the debugger gets to this data, is through the operating system. The operating system provides us with system calls. The system calls are functions provided by the operating system that allow user programs to perform privileged operations. Those operations might be reading from a file, it might be writing to a network socket, or it might be reading the memory of another process. The system call on Linux that we use for this is called ptrace. Ptrace has a bunch of different operations which it can do. One of those is peek data. So this is what a call to ptrace might look like in C. You call ptrace, you pass ptrace peek data, the process identifier for the process you want to read from, the address you want to read, and then you pass null for the last argument because we don't care about it. Ptrace is not the best API design in the world. That last argument depends on what the first argument is, and it's kind of a mess, but we make do. So if we call ptrace with ptrace peak data, we're going to get back 64 bits of data from the process that we specified the PID for at the given address. And of course, there's a bunch of security to make sure that we don't read memory from processes which we're not allowed to. I'm not going to show you everything that ptrace can do, but to give you an idea of some of the things that are supported, it can, of course, read and write memory and hardware registers. It can step over a single machine instruction. It can continue a process that we've halted before. Maybe it was a breakpoint and we want to restart it. Or it can attach to a process that's already running. All the kinds of things the low-level operations that we need to do to implement a debugger. Now, no, these are not things like set a breakpoint at some address, or even more high level, set it at a source line. For that, we need a bunch more machinery. So why don't we look at that now? Setting a breakpoint. Say we want to set a breakpoint on line 12 of petcat.c. There's two main things that we need. We need to know which machine instruction corresponds to that source line, and then how do we make the process stop when that machine instruction is executed. Let's look at that first one. In order to work out this, we look at the debug information. The debug information is data generated by the compiler that maps machine code back to the original source code. So in our architecture diagram, that's the debug information in the binary mapping the code inside the binary to the source code we wrote. Now, of course, we care about the code that's in the process, the running process, not necessarily the code that was in the executable. These are essentially the same, but nowadays binaries tend to be able to be loaded anywhere in memory for security reasons, so there's some differences between those code representations. So doing a bit more work, asking the operating system for some more details, we can change that into a mapping from the code in our process back to our source code. What does that debug information look like? Well, it's a binary format on Linux called dwarf information, and there are a bunch of utilities which can print out dwarf information, such as dwarf dump. So this is a dump of, it's part of the dump of a line table which maps the machine instructions to lines of source code. So for example, the memory address OX1886, the instruction of machine code which lives there maps to line 149 of test.cpp in this case. So this is a kind of a textual representation of the dwarf information. It's very, very compactly encoded in a custom bytecode format in dwarf, but this is more or less what it's encoding, a mapping of addresses back to source lines. Now, since we have worked out which machine instruction corresponds to a source line, how do we make the process stop when that machine instruction is executed? And there's two main ways to do this. There's hardware breakpoints and software breakpoints. So hardware breakpoints use what are called debug registers. So you would write the breakpoint address you want into a debug register. You're limited by the number of debug registers you have. On x64, that's 4. So you can't really have many of these kicking about at the same time. The real benefit of hardware breakpoints is that you can break on reading, writing, or executing a memory address. So this is how data breakpoints, for example, are implemented. Very, very handy if you're trying to track down some data corruption. Software breakpoints, on the other hand, you actually modify the code that's running in memory. They're theoretically limited, of course, up to some very high limit depending on how much memory you have and all of that. But they can only break on execution, so you can't implement data breakpoints using software breakpoints. Let's look at an example of this. Here is some x64 code. On the left-hand side are the hexadecimal representation of the bytes which make up the instructions, and on the right-hand side is the assembly instructions that correspond to those bytes. You don't need to know exactly what these do. The top two lines move data between registers, and the third line is a function call. Now, say we want to set a software breakpoint on that second line. What we're going to do is modify the representation in memory. We're going to overwrite the first byte of the instruction with OXCC. That is the opcode in x64 for the int or interrupt 3 instruction. This is a special instruction that's used exactly for implementing software breakpoints. So what int3 does is it triggers an interrupt, which is something that notifies the operating system that something has occurred. In this case, that a breakpoint has been hit. It's then up to the operating system to signal the process to stop. Say, oh, this process hit a breakpoint, we should send it a signal to say, you gotta stop execution. The debugger will be listening for events on the process, and it can intercept that there was a signal and report that to the user. So to kind of walk through how this happens, say our program counter is pointing at that first line. It will execute, the CPU will execute that first line of code. It'll go on to this one, and when it executes that, it will halt its execution because it will interrupt. The operating system will stop the process, and the debugger will intercept that. Then, when we want to eventually continue the process, what we do is put back that first byte and step over an instruction, and then put the breakpoint back, and then continue on our merry way. And that's the broad way that software breakpoints work. Of course, if you're setting a breakpoint on the entry to a function rather than on a line of source code, you're looking up slightly different parts of dwarf information, but it's more or less the same process. You query the debug information and change the memory of the running code at the relevant location. How about reading a variable? Say we want to visualize the variable mittens the cat, which might look something like this. It might have a name, which is a pointer to a C string, floofiness, which is an integer, and an age. So then we might have the cat Mittens, who has the name Mittens, the floofiness 10, and the age 3. Now, unfortunately, when this gets compiled and is actually in our running process, this looks like this. It's just a bunch of bytes. The bit at the top here, that's a pointer to the name Mittens. The next bit is 10, the floofiness, and the last bit is the age 3. So again, there's a few questions here. Where does the object live, and how should we interpret the bytes there? Again, going back to our architecture diagram, we're again looking at the debug information. Now this looks at a different part of dwarf information, not the line table, but what's called the debug info section in dwarf. And that looks something like this. Again, very heavily reduced. But this defines a structure or a type called cat. It tells us its byte size. It defines all of the members, their names, the types of the members, the byte location of those members. It gives us the information we need about the structure of a type. Then similarly, it defines information about variables. So we have a DW tag variable entry, which has the name mittens. It has a type, which will point back at that definition we just saw, and it has a location entry, which tells us where it lives. So now we have exactly what we needed. We know where it lives from this entry here, the DW at location. We know what its type is from that DW at type, which will point back to this structure type. And by looking at this, we know how to interpret it. And we can take our raw bytes into some textual representation like this. Almost at the end now. Our penultimate scenario is calling a function. Let's say we want to call the function feedCat. This is some function defined in our C++ program, and we just want to execute this inside the running process. Well, it's very simple. The first step is to write a C++ compiler. It kind of is. Like, if you're going to be evaluating arbitrary expressions and have to do things like overload resolution and implicit typecast and all of that, you basically need to ship a C++ compiler with your debugger. Of course, the bits that are kind of more interesting from a debugger perspective is how do we run the how do we call the function that's already in the running process? And the way we do that is by reading the application binary interface for our platform. So this is the API that's used on Linux systems, and it defines the calling conventions for the platform. How you need to set up registers and the stack in order to call a function. So the debugger will follow the API and pretend that it's calling a function by setting registers and the stack up in a way that satisfies the API. So that's what's happening when you do something like do expr feedCat, and it actually calls a function that has side effects and prints out a message. This is actually calling the running. This is calling the function inside your running process by faking a function call according to the API. Finally, let's talk very briefly about debugging optimized code. If you've ever debugged optimized code before, you might have seen something like this: value optimized out. This is one of a few common issues that you would find when debugging optimized code. Variable values being unavailable, being the one we just saw, having missing information in your call stack, or stepping being unreliable. You know, saying I want to go to the next line and ending up somewhere completely different because the compiler moved a bunch of your code around when it was optimizing it. One feature we have for this in Visual Studio, which is available recently, is C++ dynamic debugging. I'm only going to cover it very briefly here. If you want more information, you can go read the blog post at aka.ms/dynamic debugging. But the basic idea is we compile both optimized and unoptimized builds for your code. Then we run in optimized mode by default, and then swap out those optimized functions for unoptimized versions when needed. So that means that you get the speed of optimized functions, but then when you need that better debugging experience, you can drop down into the unoptimized versions and still have all of those variables defined, have stepping working, have your call stacks look reasonable. And this enables a few different things. You can set de-optimized breakpoints. You can step into a function and have it be de-optimized, or you can see something in your call stack and say, hey, next time you execute this function, I want it to be de-optimized. So please do check out that blog post if you're interested. That is the last scenario I wanted to cover today. So as a summary, we looked at the main architecture of a debug scenario, and then we looked at a bunch of different things that you could do with the debugger and how they broadly work under the hood. Of course, I covered all of this in about 20 minutes, so it's very high level, and if you would like more information than you could ever want to know about debuggers, please do go check out my book, Building a Debugger. Thank you very much.